Hello, this is going to be our fourth demo for the FRC LabVIEW state machine architecture, um, programming the ball simulator using LabVIEW FRC 2018. In this video, we're going to talk about the LabVIEW INI file and how you can take the settings that you set for your LabVIEW environment and move it from computer to computer. We're also going to go back into our demo and add the global stop and play around with teleop now that we have both sensors and the drive created. We'll be able to do some teleop programming. And then we'll show a little bit about rising and falling edges and making buttons that toggle with inside our teleop. And then I'm going to challenge you to build the ball intake state machine. So let's get started. So here I have LabVIEW open, and in previous videos we went into Tools, Options, and we went through and selected a few items where we unchecked this box and unchecked that box so that our LabVIEW environment did more what we asked it to do or we wanted it to do. If you scroll down here, you'll see there's several options that you can set to set the LabVIEW environment up the way that you want it to. So one of the ones that's obvious is like the grid here. So if you wanted a grid on your block diagram and you wanted to be able to snap to different locations on your block diagram, you could check this box, you could click OK, and then when we create a new VI, you'll see there's a grid here on our block diagram. And if we go back to Tools Options, we can scroll down and we can shut that off. And there's also a grid setting here for front panel if you wish to put a grid on your front panel as well. And we put a lot of work and effort into getting the environment set up the way that we want, like our quick drops. Remember our quick drops that we had? We spent a lot of time getting our quick drop shortcuts working the way we wanted them to. And then we go to a new computer, and that computer doesn't have all these options, and we got to set it all up, go into our Tools Options and set it all up again. So if you find that you are moving from computer to computer, like you're working at the school computer one day and you're working on the robot computer on the next day, and you want your settings to go with you, there's a file called the LabVIEW.ini file that's located where LabVIEW executable is, and you can copy that file and move it and bring it with you from computer to computer, and I'll show you where that's at. So I'm going to close LabVIEW here, and I'm going to just bring up my PC. So normally LabVIEW is stored on the C drive, but wherever LabVIEW is installed on your PC, you open that drive up, and we'll go to Program Files x86. That's where most of the 32-bit applications are stored. And then there's a folder called National Instruments. That's the company that makes LabVIEW. And then you go down to LabVIEW 2017, which is what we're using, but if you're in the 2019 season, you'll use LabVIEW 2018. And if we open up the LabVIEW folder, there's this LabVIEW.ini file. And it's just a text file, so I'm going to open it up and show you that it's just a text file. It's got an .ini format, which gives it, you usually have section heads and brackets here, and then inside the section is different, what's called keys, so it gives you some kind of name equals some kind of value. And you'll see this is my custom file that I've set up, and in here you'll see there's a thing called quick drop. So these are all my quick drop shortcuts put in text, in a text format, and all the other settings that I want my environment to look at are here in this INI file. So what happens is if you don't have your INI file, so I'm just gonna rename this to MB. So now LabVIEW look specifically for LabVIEW.ini. If it doesn't find it, it will create a new one for me. So I've renamed my LabVIEW.ini, and I'll just show you that without my INI, I lose all my settings that I... Okay, with LabVIEW open, I'm just going to generate a new VI, and you see put a front panel grid on, which I didn't like. And then if I drop an icon, you'll see I get icon terminals again. And if I grab something and accidentally grab a capital and I do a feedback node comes in. And I spent all that time previously, and then I don't have any of my quick drops. So if I control space and try to bring my cluster unbundle, see, I don't get that either. So that's what's happened if you don't bring your INI file with you. You have to go back and set all those settings back up again. And now, and you'll see LabVIEW created its own brand new default INI file. So I'm going to delete that, and I'm going to bring mine back. And then I'm going to reopen LabVIEW again. Okay, now that I have LabVIEW open with my personal LabVIEW INI file back installed, and I open a new VI, when I drop a control, I get my icons, and if I do a feedback, I don't get a feedback node, like such. And all my quick drops are back. Unbundle by name and my bundle by name are still there. So that's the LabVIEW INI file. Again, I would copy that to a thumb drive or put it on your Google Drive. And every time you go to a new computer that you haven't used before, just copy your LabVIEW INI file onto the National Instruments folder. Again, that folder is, go to the C drive, Program Files, National Instruments. You can type N and it will take you to the ends. National Instruments, L for LabVIEW, and the version of LabVIEW that you're using, and then your INI file. If other students are doing this as well, make sure you rename the LabVIEW INI file to their name or something before you bring yours in, so you don't destroy theirs, so they can bring theirs back too. Alright, so we're going to continue programming our ball shooter simulator. And I have my demo 3 folder here from my last programming exercise, and like before, I'm going to copy it and label it demo 4. So to go get demo, if you don't have demo 3 already created, you can go to this bit.ly link and download it. It's my Google Drive that has all the demos on it. And we'll open up demo 4 and start with the project. And we're going to save it and call it demo 4. And now that our project's open, we're going to do a file save as, rename it to demo 4. Okay, so we have our project open, and I want to show you how we're going to add the global stop. So if we go to our periodic tasks and do a little bit of review, and Control E, I'm going to go to my block diagram. We have our 4 loops that we've created. So I'm noticing that my icon isn't right for my drive. Seems to be an artifact of some previous code I was writing. So I'm going to go in here and fix the icon for my drive. So I'm going to double click on the front panel, double click on the icon to bring up the icon editor. And File, Save All. And then my loop looks good now. So if we go to the block diagram of our drive loop, and in all of our loops we have this global stop here. But we haven't programmed anywhere yet in our main VI where this global stop gets set. Right? So I'm going to go back to my robot main. So I'm going to go to the project, Control Shift E, and I'm going to find my robot main. Where I'm going to put my global stop is in the begin I'm going to set my global stop to false. So what my global stop does is it stops all of my loops. And the question is when do I want to stop all of my loops? Well, when this top loop finishes, I'd like to tell all my loops down here in my time tasks to also stop. So let's put true to global stop when I come to finish, and let's make it false in begin so that I set it to false so none of these loops stop prematurely. We only want them to stop when this top loop has finished. Okay, so I'm going to go into begin, and I'm going to add my global stop in here in begin, similar to how the FRC template sets a robot mode. In here in begin, we're going to set the global stop to false. So let's find our global stop. Our global stop is in the utilities of the VIs that I brought in. So I'm going to go back to my project, Control-Shift-E, and if we go, there's my systems folder and templates and utilities folder. Under RoboRio utilities, there's your global stop. I'm going to just drag it here onto my block diagram. Make sure it's changed to a right. It is. And then I'm going to create a constant and set it to false. So that makes sure that the global stop is set to false before all my loops are called. And then if I go back to robot main, we're going to set a global stop in here once everything is finished. So another way we can bring in a global variable is through a VI. So we're going to right click and we can say select a VI. And we can go to our RoboRio template and utilities, RoboRio utilities, global stop, and click OK. That's another way to do that. And I'm going to create a constant and say true. So when this loop gets to finish, the robot mode goes to finish, we're going to call our global stop, and then all of our loops in our time tasks will see our global stop go true, and we will go into shutdown. Shutdown state goes into shutdown. The global stop will stop the loop. We will go into shutdown, do our final action, whatever our final action is in shutdown, and then that loop will stop. Right, and then let's do a save all. Okay, so now we've added our global stop. So the next thing I want to do is show you some tricks in Teleop to help us take our Teleop joystick commands from our game controller and start commanding our drive. So let's go and open our Teleop. So over here in our robot mode under Teleop, we'll open our Teleop VI. So just a review, we're reading our axes and our buttons here from our game controller loop, come in as arrays, and then we pull off buttons and axes as we need. We put them into the global variables of the commander, because Teleop is the commander when we're in Teleop mode, and we take those axes and we modify them if we need, and we put the values into our command globals, and those command globals then write to our actuators. So in this instance we set our mode, either Teleop or stop, based on a button that we're pressing, and then we move the axis values into our left and right and forward and back inputs. When we are in Teleop we use those inputs. When we're in stop we do not use those inputs. If you remember, that's how the drive was programmed to work. So one thing that's a little bit of a pain is we have to remember what number buttons correspond to what buttons on our controller. So if we go back to our driver station, so with our driver station open, we again go to our USB tab, and these are all our buttons. And I always forget which button is what. So if I want, this is my right bump switch button, and I gotta go 0, 1, 2, 3, 4, 5. That's 0. That's button 5. And then I never remember if I push my joystick buttons down what buttons those are. 0, 1, 2, 3, 4, 6, 7. That's button 8. So it'd be really nice if I had a table or something that would tell me. So one thing we could do is we could create a table. We could say, you know, index 0 is my green A. Index 1 is my red B button, and so on. Right? And so we create this number name list, and then we have it there to look up. But there's also another way to do it that I prefer, and like whenever we have a number name list, what does that remind you of? Well, it should remind you of an enum. So if we created an enum for all our buttons, and we put the first one as green A and the next one is green B, its index, its number would actually be the index. And because enums are integers, we could wire that here to our indexer. We would know the name of the button, and it would automatically pull that out. We can do the same with our axes. So we would know every axis, and then if our driver decided later that they wanted to change the button that they use, it would be simple pull down, similar to this, and we could select the button and then just recompile. Alright, so it's easiest to build a enum from a front panel, so let's go to any front panel and right click, and we'll grab an enum. Alright, whenever we start an enum, we immediately want to make it type def, so we're going to right click and say make type def and open type def. And we go into our control editor. Right? I'm going to do my axis select. I'm going to call it enum axis select. And I'm going to save it in my RoboRio folder, and I am going to create a new folder called Teleop Support. So I'm going to right click, new folder. If you want to make a different folder, feel free, or put it in with your other stuff. And these are the VIs that's going to be specifically run in Teleop. We can make other folders later. Right, so I'm going to open my Teleop support folder, and this is going to be enum a axis select control. Okay, so I'm going to start to build my enum. So the first thing, what I want to look at is as I move my joystick. So I'm going to move my joystick left. You see that my value goes negative, and my right, my value goes positive. And if I go my Y, if I go forward, you see it goes negative, and backward goes positive, which is a little bit surprising for me. So that's another thing maybe I should document, is that not only the name of that axis, but what negative and positive mean. So I'm going to edit my items, and my first item is 0, and so I want to label this 0. So this is going to be left, and instead of saying X, I'm going to say left and right, but I'm going to say left -1 and right +1. And then if I go down to my index 1. Forward will be negative, backward will be positive. And then if I look at my trigger, I'm going to go with my left trigger. That's going to be index number 2, and it only goes from 0 to 1. So it doesn't go negative, so that's something that I might want to remember too. So left trigger, and I'm just going to say 0 to 1. Alright, and then I'm going to fill in the rest here, and then we'll move to the buttons. Okay, so I have all my values entered. I should have 6 items, 0 through 5. One thing I had to do is kind of clarify a little more that this is the left stick. Left is -1, right is 1, left stick forward is -1, back is, and then I had to clarify the right stick as well. So very descriptive and helping the programmer know exactly what that axis is. All right. So I'm going to click OK. So I have my items, and then I find the biggest one. I usually size it to that so it fits, and then I'm not a big fan of having increment and decrement, so I just right click, go to visible items, and uncheck that, and let's make an icon for it. Okay, so we've created a new enum, made it a strict type def, saved it in our teleop support folder, made an icon, and apply changes and save all. Alright, and let's find it on our block diagram. Right click, find terminal, and we're going to change this to a constant because we're going to use it as a constant. Change to a constant. Alright. So now we don't have to remember the numbers of our axes. We just select here the one we want, because this actually represents 0, which will be 0 axis in our when we index it from the array, and it will send the 0 axis. But we don't have to remember the numbers anymore because we've captured the numbers and the names together in an enum. Alright, so I'm going to take this and move it up a little bit. So I'm going to highlight it, and I'm going to hold down the shift key, and I'm going to drag it up, and you'll see it'll drag it in a straight line. So, and I'm going to control, and I'm going to copy this 3 times because there's 3 items I need to, 3 axes I need to, and then I'm going to clean this up. So I'm going to select all of them, and I'm going to go up here and just arrange and align left. So kind of neaten it up, keep it neat. Right, so this one is 0, so our first item, and we're going to wire it here. So that's going to be our left. So you will get a coercion dot, but that's not a big deal. Levy will handle that. And then this is going to be 1, 0, 1. And this is 2, and this is 3. So 0, 1, 2, 3. So now it's a very much easier to know what axis is going to left, right, because we have it right here. It's our left stick. Left is negative, right. So we also remember, hey, when I move it left, will I be getting a negative 1 or a positive 1 here? Well, we wrote that in our enum, and that helps us as a programmer not to make mistakes when we are in a big hurry and they've asked us to change axes, or they've asked us to put it someplace else on a different game controller or something. We have easier documentation to quickly read and quickly know. Right, the next thing I want you to do, I want you to pause the video, and then I want you to make an enum of all the buttons on the game controller, or your game controller, and then come back and replace those with where we're using this button, and here we're using our stop button. And I'm going to do it as well, but I'm going to speed up the video and make it go really fast, and then we'll come back when I'm done. Okay, so I've finished my list. One thing that I found useful is because they don't have the buttons labeled, it's kind of hard to remember what's the next one is. So here's my right bump, which was 5, and I held that down, and then I would play around with the buttons until I found the next one after it. So I went to my pad and pressed my start button, and then I pressed my back button. Okay, my back button is the next one. So then after right button, I would write my back. And then I'd hold my back button down, and I would go to start and see that that was the next one. So then I know to write start after that, and then same, this is my left stick press, and then my right stick press. So that's one little trick I figured out when trying to get this order of, so this order really matters because you want to assign the correct name to the correct index on your buttons. And because the driver station doesn't give you names like it gave you the axes, you kind of got to do a little more investigating and figuring out which each button is. And this, which is what makes the enum even more powerful for the buttons, is because it's harder to remember what button is what index, because anywhere is it written. So making this enum should really help us. So I'm done with my list, so I'm going to click OK and go through the final steps and put this on Teleop. Okay, so I've saved it by button select enum in with my Teleop support folder. I made an icon. I removed the up and down arrows and make sure it fits, and so we can just drag it right onto our block diagram, and then we gotta apply changes, save all, and close. Alright, so now I have a button enum, and 0, 1, 2, 3, 4, my left bump is now my brake. That makes it very obvious when I push my left bump, I go true, and that's my brake for my drive. I'm going to copy this down here, and that's 0. So my right read pad button A is the button that changes my servo angle for my shoot servo. So that's my fire button to fire my ball, is my green A. So again, making Teleop, I'll delete this here, making Teleop much more readable and much more quickly changing. The other thing we can do is, since this is so readable, we could actually take these values and put them up to our dashboard. We'll make a dashboard in later demos, and we could have the driver at dashboard time. He could go into a dashboard and he could select these buttons, and then we transmit those values down through these network tables from the dashboard, and then these buttons would work, and the driver could change whenever he wanted to, and we wouldn't have to go in and change code. And we'll play around and do that in a future video. Okay, so the next thing I would like you to do, so if we come back to time tasks, I would like you to pause the video, and I would like you to build the um, scoop. They call it the scoop, but it's the intake motors. Build a loop, an actuator loop for the intake motors, um, and set them to turn on. Choose a button to turn them on, and if you want, you can use one of the triggers to set the throttle, or if you want to I'm just going to have a button turn them on and turn them off. Okay, so when we do that, we're going to turn on and turn off. That's called a toggle, and it's not usually obvious how to make a toggle work. What we want a toggle to be, it works like a ballpoint pen. So when you press or a clicker pen. So when you press the pen, the tip of the pen goes out and stays out. And then when you click it again, the tip of the pen goes in and stays in. So we want to push a button, and that button turns something on and keeps it on. And then when we push the button again, we want it to turn off and stay off. Okay. So I've created a VI in our utilities called Rising Edges, I believe. So let's go to our Control-Shift-E and go to our project, and then go under our utilities. And you have this utility called Detect Button Change. So we're going to drag it here on the block diagram and also use this in Teleop. And we're going to wire this to our button array. So what I have is 5 different outputs coming out of here. This one is just the straight value out. It's the same value in as value out. This one tells me every time there's a rising edge. So every time a button is initially pressed. So previously it was off, and this iteration of Teleop it's on. Gives me a rising edge. Then we have falling edge. And these last two are what's called toggles. Right? So if we want a toggle, we can take this array and we can index off of it just like we do our other ones. And when that button is pressed, that output will stay on, and when that button's pressed again, that output will shut off. So this is toggle on a rising edge on an initial press, and this array represents toggles on a falling edge. So you can press the button, hold the button, and then release it, and it will just stay on. You'll press the button, hold the button, and once you release it, it will go off. All right. So I'm going to open this up, and I'm just going to run robot main, and we'll bring an index here. I'm going to drag copy an index, and I'm going to wire my toggle array to here, and I'm going to copy my button enum, and I'm going to make this my joystick, one of my joysticks, my left joystick. So my left joystick press. And again, I don't have to remember what number that is because my enum takes care of that for me. And I'm just going to create an indicator on it so that we can look and see how the toggle works. So I'm going to create an indicator and just call this toggle. All right, and then I'm going to double click on that. It'll just show me here in Teleop my toggle. All right, so I'll put this over here, and I will find my robot main, and I will run it. Robot main and run. And enable. Okay, so here's the Boolean states that I've created. And Teleop's going to run real fast, so you may not see the rising edges. They'll only be on for one iteration of Teleop. Okay, so I'm going to push my 0 button, See my 0 button's pressed, and you'll see these flash on for just a brief second. Right? Falling, rising is too fast. But down here you'll see here's my toggles. So I'm pressing, so it goes on, and I release, and on the release my toggle bolt goes on, and you'll see that these stay on. Now these are again running in teleop, and then if I want to shut that output off, I'll push the button again, press, the toggle went off, and release, this toggle went off. Okay, so here's the toggle indicator that we created in teleop. Again, I'll press, release. All right. Now, if I use the button I said was my left joystick, if I press my left joystick, press, see the toggle went on, release, and the toggle on stayed. And I'll press again to shut it off, press again to turn it on. So that's kind of how a toggle works. If you're interested in what is the logic behind a toggle, we can look at the block diagram here, and I tried to explain it as best I could. Essentially, it's if you've taken logic, it's an exclusive OR gate where we look at the rising or the falling edge of our button coming in, and we look at the previous output value of our toggle. And kind of here are the truth tables. So an exclusive OR says if they're different, you get a 1, and if they're the same, you get a 0. And you can examine that. I won't go into exactly how to do that, but here's as much of the truth tables and stuff as I can explain how it's done. Again, you need the rising edge or falling edge, and then you need the previous value of the toggle, and if you exclusive OR those, that's how you make a toggle work. Okay, so going back, I'd like you to pause the video, and I would like you to build, if we go back here to time task, I'd like you to build the code for the ball intake. So go and copy an actuator loop and fill it all in, and turn on the left and right motors and control them in some way. For instance, you can control them the same way here. We can use button 1. This is all going to be moved up to teleop here. We're reading the buttons up in teleop, and we're going to write to a global variable that will make these motors run. So notice the code that one runs forward and the other runs reverse. Make sure that works in your code. And then once you create the loop, put the loop in time tasks like we did here with the drive, and then test it and kind of zoom into your robot and make sure that the motors are spinning the opposite direction, and then see if you can intake a ball into your scoop. All right, so go ahead and pause the video and build that loop, and I will build it as well, but I'm going to build it super fast with the video sped up so we conserve a little time, and then when I'm done I'll come back and talk it through with you. So brief pause here. I used the LabVIEW graphics to quickly draw up a state machine. And again, the way you do that is all the decorations are on the front panel. So you have to have the front panel, you pull off the decorations off the decorations palette, and you can actually pull them onto the block diagram. So I pulled circles and some arrows, and then if you double click in blank space, you can create a free label, and then shift right click, you can get the paint tool, and I can color them. So startup, we immediately go to idle, but we send the stop intake action, and then we look to see if our enable is true or false. If false, we continue stopping the intake. If we are enabled, we go to running, and if we're still enabled at running, we run the intake action, and that's just going to take the speed control from the command and send it to the motors, and we keep in running until enable goes false. We stop the intake and go back to idle, and here we look for global stop, and we should have another arrow coming from idle to shut down with global stop true. All right, I will continue. I will now implement this state machine for my state cases and my action cases. Okay, so I've been completed the intake actuator code, and let's review. So I ran through that very quickly. I sped the video up pretty fast. So what I'm going to do is I'm going to create a separate video that just shows me doing this in real time. Um, so those that want to review or follow along slower, I'm going to have a slower version of video just creating only this state machine. But let's review, go through it. So at the beginning we open our two motors, our left and right motors. They are PWM 7 and 8. We had to create constants to put in our cluster so we could bundle those two in. We created a command cluster here from that teleop or autonomous will write to command the intake, and in there is two items: the speed, which is the 0 to 1 value, tells how fast we want to spin our intake motors, and an enable button that will turn the intake on and off. And we built a state machine with 4 states and 2 new actions. And there's our state machine. And here are our 4 states. Startup. We immediately go to idle, and we do a stop intake action. Idle, we look at our command, enable, and if it is true, we go to the running case, and if it's false, we stay here in the idle case and we continue to send stop intake. If we are running, again we look at the command. If it's true, we stay here in running and we send the run intake action, and if false, we go back to idle and we set the stop intake action before we get back to idle. And then we have a shutdown, continuing shutdown. That will shut down the loop anyways, as we will send a stop to our loop, and our last action will be stop intake. And for our actions, we have our basic 3 that we always just keep there because they may be useful. For stop intake, we set our motor speed to 0, and for run intake, we read the speed from our command global cluster, and we write it to our motor speed 1:1. If our motor goes backwards or does the opposite of what we want, we could invert this number, or we could invert it here at our set outputs, whichever. We have to test it to know for sure. And then our last section, we write all our outputs. So we set our motor values. One we run one direction and one we run the opposite direction at the same motor speed. And then we write those values, output values that the motors are running at, to global variables because somebody may want to read those. And we put them back, all these items back in our cluster. And then we also run a bunch of displays here for our front panel. So if we're trying to debug, we can quickly open this front panel and we can see what our values of our intake are. And if it's supposed to be enabled and it's not, we can see that as well. And then finally, when the loop stops, we close our motors. Now the other code did not close the motors, so to find those motor close, we have to go to our library and robot drive, and then there's a motor folder here, and with all the motor direct motor VIs, and there's your motor close. And the last thing I want to do is create an icon. Okay, and I'm going to remember to take my actuator loop and put it in my periodic tasks. So let's go find periodic tasks. And let's go up here and put our loop. I'm going to select the VI. I'm going to go to my RoboRio, my systems, my intake, actuator loop, and place it in there with the other. So now I have 5 working loops. And the last thing to do is test it. So bring up the driver station. And open robot main. Oh, I forgot I need to remove these items. So this looks like scoop speed coming in from an NT. We're going to move this to teleop. We're going to move all this to teleop because this is only going to be done in teleop. And we're then this speed value here and this enable here are going to be done in teleop, and we're going to write those to the command globals for our intake. So I'm going to erase these values, these VIs here. I've already removed them from begin, and I'm going to cut this code and we're going to go paste it into teleop. Alright, and I'm going to go get my command global for my intake. Select the VI. Global command actuator. And I am going to index off of my game controller. Looks like you can have the global in multiple spots, but I don't typically like to do that because it may be confusing. So I'm going to bring the array here, and they already have button 1 set, but I'm going to use my button enum 0, 1. It's going to be my red pad, my red B button on my controller. And I'm going to create a constant here and then do an unbundle by name. Double click to show the icon, and then I'm going to do my unbundle by name. Wire the middle terminal first, and delete this wire. So this is going to be my speed. It's coming from a network table, which may come from a dashboard later. And this is my enable. Like so. Okay, so what's going to happen is I'm going to push my red B button, and I'm going to have to hold it down in order for my intake to run. And as long as I have my B button down, my intake will run. As soon as I release my B button, this will go false, and my intake will stop. And that's not really what I want. I'd really like to put it on a toggle. I'd really like to press my B button to turn the intake on, and then press my B button again to turn the intake off. So we can use our Boolean state here, and we can index our value off of our toggle, and it will work for us. So I'm going to remove this code here. So this was just example code to show that it worked. And I'm going to move it up here, and I'm going to bring my Boolean array here. Again, that's from my buttons. And then I'm going to disconnect this. Move it forward a little bit. And then I'm going to bring the toggle on rising edge, the whole array into there, and I'm going to tap off the item that would be the red B, and now I have a toggle going into my intake. So now when I press the red B button, it will toggle it on, enable, and then toggle it off. Alright, so I'm going to file save all, and let's run and see if that works. So I'm going to find my robot main, run my robot main. I'm going to zoom into my robot so I can see these wheels right here. Maybe rotate a little bit. Oh, I gotta shut it off to rotate. Again, I'm going to control, hit my shift key and zoom in this way. Then hold my control key and go up. And then rotate. That should give me a good angle. And zoom in. And control for pan. Zoom in. Pan. Alright. So I can see those wheels. Those are my intake wheels. Let's bring in my driver station and enable. See, they're not running, they're not spinning. I don't expect them to. And I'm going to go to my teleop, and I'm going to put some probes. So if I hover over wires, see this little P tool? I'm going to probe on that, and you'll see that my speed, my scoop speed, by default is set to 0.7. So that's pretty fast. But they're not spinning because in my state machine I said you had to enable. So let's put a probe here on my red B going into my enable. Right now it's false. Now my expectation is when I hit the red B button, I should turn on and stay on. So I pressed and released, and you'll see that the toggles kept the value true. So now I'm in enabled. Now let's go look at our thing. And not quite clear, but looks like my wheels are spinning. So to prove that, let's go to our loop. So let's go to time tasks. So I'm going to go back to my project, open periodic tasks. We're going to open our actuator loop. You see our values are 0.7, and if I push my B button, it toggles the enable off, and all my values go to 0. So that's what I expect. And if I'm still wondering if that's true, I can come down here to my set outputs, and I can take my probe tool and I can probe on those. And both those are reading 7 and -7. Okay. Now when I come back to the robot, it does look like they're spinning now. So I can drive the robot around now and see if a ball will come in. Alright, so I'm going to go back to zoom into the robot, zoom out a little bit, see if I can find a ball somewhere. And let's see if I can shoot a ball. So if I remember, I programmed the ball shooter to be my right trigger for speed, and my green button to release a ball into the shooter. So I'm going to throw a couple balls, as many balls as it'll let me. Okay, so I've been driving around a while trying to catch a ball in my intake, and it's pretty difficult. So I'm going to change my driving configuration to see if it's a little bit easier for me. So I'm going to go to what's called a stick and rudder configuration. So my left-right is going to be my right joystick instead of my left joystick. So I'm going to hit right, left, right. And my forward back is going to be my left joystick, forward back. So what this allows me to do is to control forward back, my speed with my left thumb, and drive right and left with my right thumb. Similar to like a car where you have one's controlling the steering and one's controlling the throttle. And let's see if I have any better luck trying to catch a ball in my scoop with this driving configuration. So I took and emptied out my ball chamber just so I have a better chance of picking up a ball. And you see if you go really slow, you eventually can get to one, get one in the hopper. But it takes a lot of practice, and the more balls you have, the better odds you have of finding one. I found that you needed to, it's easier to go after balls that are standing still instead of that are rolling, because they tend to roll just as fast as the robot can drive. So you'll see here I get the blue one to go in, but I swat the pink one just a little bit too much and it starts running away. Here I'm trying to corner them in the corner to see if I can push them into the corner, but just touching the balls and they just go flying. So I come in close, come in really slow, try and pick up the pink one. Just able to get it, but I bumped the green one too much. Try to catch it on the way back. And get it. So this is quite a challenge. So that's our intake actuator state machine. In the next video, we're going to move to get a little more advanced. So we're going to work on the shooter, which is this code here for the default. We're going to combine the releasing servo with the drive motors that throw the ball, and And if we go to periodic tasks, we'll also work on building an agitator. And that's the thing inside the hopper that moves the balls around and guides them into the shooter. We'll make a separate actuator loop for this, and you can see there's lots of logic here. We'll talk through this logic and decide if we want to implement this or we want to implement a different version of it. So thanks for watching, and hope this helps you in your building of programming of robots. I'll see you at the next video.